Let's take a few moments to look at substrate binding in more complex reactions involving two substrates and two products. We also want to find a more accurate way to determine Vmax and Km. Reactions involving two substrates and two products are referred to as bi-bi reactions. Though they share this in common with each other, yet the mechanism of the reaction can vary. An ordered mechanism involves binding substrates and releasing products in a specific order, as illustrated here. In a random mechanism, substrates bind and products release in no particular order. A special type of bi-bi reaction uses the ping-pong mechanism. There is an order of substrate binding and product release, but the enzyme becomes covalently modified in the process. The first substrate, A, binds, forming the EA complex. This is converted to product P, but the enzyme has been modified, indicated by the prime symbol. Product P is released prior to binding the second substrate, B. B is converted to product Q, thereby returning the enzyme to its original unmodified state. Release of product Q is the final step. This type of mechanism is common in enzymes that transfer a functional group from one molecule to another. In an effort to more accurately determine the values of Km and Vmax, Drs. Lineweaver and Burke derived a modified form of the Michaelis-Menten equation. They simply inverted each side of the equation, as shown on the top left. If we separate the compound fraction and rearrange terms, we get the final form of the Lineweaver-Burke equation. You may notice that this is simply the equation for a line. If we plot 1 over velocity on the y-axis and 1 over substrate concentration on the x-axis, the slope will be equal to the value of Km over Vmax, and the y-intercept will be 1 over Vmax. We can see the graphical form of this equation in the lower right. We do indeed see the form of a straight line with a positive slope. It crosses the y-axis at a point equal to the inverse of Vmax, and the slope has the value of Km over Vmax. Notice that if we set y equal to 0, we get the x-intercept, which is negative 1 over Km. Now we have a more accurate way of determining our Km and Vmax values. We can plot 1 over velocity versus 1 over substrate concentration at multiple substrate concentrations. Then we can do a line of best fit from which we can derive our kinetic constants. Although we now have more accurate ways of determining these values, this type of double reciprocal plot is still used to demonstrate enzyme kinetics. We will find it a useful tool when we begin to look at enzyme inhibition patterns.